This is exercise 12.4, box culvert utility model and analysis. In this exercise, we will lay out a box culvert and then analyze the hydraulics so that we can correctly size it for the proposed flows. So we'll start off by continuing to utilize the same RDWYII BC drainage model DGN file. Let's go ahead and turn off the RDWYII BC existing drainage DGN reference file. Then select the default view in the lower left corner and switch to the drainage and utilities workflow in the upper left corner. So let's go ahead and open up the Place Node tool under Drainage and Utilities Layout and Layout. A warning will display asking if you want to proceed with embedding files for drainage and utility projects in the design file. So go ahead and click Yes and give the software a few seconds to load the drainage standards from the library. You should also get a compact database alert asking if you want to proceed, so go ahead and click No on this one. It is recommended to always click No unless the database, such as the drainage DGN lib, has been updated and needs to be compacted. And you should get this compact database alert twice. Press No both times. So as a reminder, the previous two alerts are only seen when creating a drainage model in a new file. All drainage modeling tools will now open the first time in this file. So now let's go ahead and reopen that Place Node tool, and we're going to set up some of the settings. Note that the nodes in this part of the model are just used to facilitate the drainage analysis. The box culvert model with wing walls that is accurate to TDOT standards will be created in the next exercise. So in this Place Node dialog box, we're going to set the feature definition to begin box culvert under Node, Stormwater Node, In-Wall, Cross Drains, and then box culvert. Begin box culvert. We'll leave the name prefix as it is, and we're going to set the elevation is the insert. We're going to leave that toggled on, and we're going to set the elevation to be 691.77, which this should match the same elevation at the begin invert in the survey. And then we're going to leave the rotation mode as absolute, but we can ignore the rotation angle since we're just placing a circle. So the first prompt here is asking for the reference elevation, so we're just going to right click here. Now we're going to snap to the start of the box culvert alignment drawn in the previous exercise to define the head wall. So left click to accept the node location on the upstream side. Then left click again to accept the rotation mode, and then left click to accept the rotation. And again, note that for this node, the rotation angle is insignificant since it is circular. So now we're just going to repeat those last couple steps to place another node at the downstream side of the box culvert. So go ahead and select the in box culvert feature definition and set the elevation to 689.98. So next, let's place the box culvert between the two end walls. So open the Place Conduit tool under Drainage and Utilities Layout. And then we'll be analyzing the existing 8-foot by 8-foot culvert to see if it's sufficiently sized to convey the proposed flows. So within this Place Conduit tool, we're going to set the RCBC as a feature definition, which is under Conduits, Stormwater, Culvert Pipes, Proposed. And then we're going to set the description to 8 by 8. And note that if 8 by 8 option is not available under the description dropdown, close the file and clear your user preferences, and then it should appear. Now we're just going to select the upstream and downstream nodes as the start and end nodes to place the conduit. And notice that the width of the box culvert is represented by the double lines, or the wall, and it is seen because the active file 3D reference is turned on. So now let's go ahead and turn off that 3D file, so the RDWYII BC drainage model DGN default 3D. We're also going to turn off the survey reference file. Then we should only be able to see the center line of the proposed box culvert. So now within the Explorer, under Drainage and Utility Models tab, notice that the drainage features are now populated. And refresh the Explorer if they do not appear. The following steps discuss how to input flows for this culvert. So for the hydraulic analysis, this exercise obtains the design flows from the USGS stream stats. As an alternative, you can calculate the runoff draining to this culvert using the regression equations mentioned in the TDOT hydraulics manual. A TDOT survey file would also provide the drainage area for the culvert. You would need to calculate the time of concentration if relying on ORD to calculate the runoff. And refer to exercise 5.11.1.5 in the SUDA ORD manual on how to input these time of concentrations or calculate the composite TC values. And then once the flows are determined, it is recommended to check if the Q50 is less than the 500 cubic feet per second constraint. So the design storm for which the box culvert will be sized depends on several factors, such as whether the roadway is owned by TDOT or local jurisdiction, or if it's crossing in the FEMA zone. You'll need to follow the TDOT hydraulic manual and Chapter 4 of the TDOT drainage manual to determine the design storm event. For this exercise, we will have the box culvert be designed for a 100-year storm. So the design storm flow and the contributing drainage area for the current crossing has been obtained from the USGS stream stats. For reference, the contributing drainage area and the Q100 cubic feet per second are provided in the figure in the manual for step 15. So from this data, we can determine that the box culvert will need to accommodate 464 cubic feet per second without overtopping the roadway to meet the 100-year flood. Also, we meet the 500 cubic feet per second constraint, so would not need to send this culvert to TDOT hydraulics. So it is recommended to compare the area obtained from USGS to the area provided by TDOT survey to ensure that they are not vastly different. So we see in the image in the manual on step 17 that the highlighted area represents the area contributing to the culvert location. Notice that the drainage area boundary closely matches the boundary obtained from the USGS stream stats shown in step 15. So now within the Explorer, under the Drainage and Utilities model, right-click on the Begin Culvert 1 node and select Utility Properties. So under the Drainage tab, scroll down under Flows. And here we want to key in the 100-year flow of 464 cubic feet per second. And note that if the utility properties do not populate, close the Explorer and then reopen to refresh. So next, within the Explorer, under the Drainage and Utilities Model tab, right-click on the RCBC1 conduit and select Utility Properties. Under the Drainage tab, scroll down under Physical Culvert and set the Is Culvert fill to True. So now some more fields will populate. So since the box culvert will have wing walls, we need to set the culvert head wall and the culvert end wall fills to 30 degrees to 75 degree wing wall flares. Also, if the utility properties do not open using this method, in this step, select the conduit in the plan view and then open the utility properties from the ribbon, which is under Drainage and Utilities, Utility View, and then Element Views. So in the closeout of the utility properties, and now we need to analyze the box culvert hydraulics capacity using the most applicable option. So go ahead and open the Scenario Manager under Drainage and Utilities, Analysis, Calculation, and Scenarios. So expand the 2-year HEC 22 Analysis Shelbyville folder, and then right-click on the 100-year HEC 22 Analysis Shelbyville and select Make Current, which will add a red check mark next to the scenario. And here, be sure to select the Analysis Shelbyville and not the Design Shelbyville. And then close the Scenario Manager once you are done. So next, open the Compute Scenario tool under Drainage and Utilities, Analysis, Calculations, Compute, and let the software compute the selected scenario. A GVF rational calculation summary has now been generated. So go ahead and close this window, and then you'll likely see a Civil Message Center open in either the side or the bottom of the screen. And then go ahead and close that window as well. So now let's create a profile along the box culvert so that we can view the hydraulic grade line, or HCL. Let's first deselect that Use Active Feature Definition within the Feature Definition toolbar, which will allow us to select the correct feature definition for the profile run. So now within the Explorer, under the Drainage and Utilities tab, right-click on the profile run and select Utility Run from Links. So within this dialog box, select the Props Storm Sewer feature definition under Linear, Profiles, Profile Runs, and Design, and set the node draw type to Box. Then select the Box Culvert Conduit as the first link and then right-click to reset. The trace profile should be highlighted in orange. And then notice that a profile run has been created within the Explorer. But before we open this engineering profile, we need to go to File, Save As, and create a copy of the current DGN file. And then we will work within the copied file for the next few steps. Note that we need to copy this file due to the defect in the 2022 Release 1, where after opening the engineering profile, the file becomes unusable beyond that point, such as it cannot be reopened. So if you're using the 2022 Release 1.1 profile, or Bentley has resolved the issue so that there's no need to copy this file. But for me, in 2022 Release 1, we're going to go to File, Save As. And we're just going to save a copy, so I'm just going to add a -copy at the end and press Save. And with this copied file, you may get that compact database. So again, press No. So now the copy file is open. I'll open up some of these tabs again under the Drainage and Utility Model in the Explorer tab. So on this profile run, right-click on that profile run and select the Open Engineering Profile. This profile is shown along the pipe length and not along the project's alignment. So in the Engineering Profile window, review the nodes, conduit, and ground elevation and the inverts to verify that the inlet and the pipe are connected correctly in the direction of flow along the box culvert. This blue line represents the hydraulic grade line, or HGL. This profile shows the box culvert is currently not overtopping the roadway and is able to handle the flows. This also shows that the existing culvert is correctly sized for the 100-year flow reaching the box culvert. Note that if this culvert was sized incorrectly, you would need to change the size of the box culvert until it successfully conveys a flow. So furthermore, you can open the Flex Tables tool under the Drainage and Utilities, Analysis, and then Analysis Views, and then we can view the results there as well. So within this Flex Table window, double-click on the Conduit Table, T-Dot, Flex Table under the Drainage tab, and you should see this window. Scroll over to the velocity feet per second, and then we can see the outlet velocity is 16.75. So this outlet velocity is 16.75. This is below the T-Dot max velocity of 20 feet per second and would require a significant treatment at the outlet to mitigate the downstream erosion. Refer to Chapter 6 of the T-Dot Drainage Manual for further details regarding velocity limits. Since this flow is above 12 feet per second, an energy dissipator would be needed. So refer to Chapter 9 of the T-Dot Drainage Manual for further details on energy dissipators. But for this exercise in this manual, we're just going to ignore the need for energy dissipators. So I'm going to close out of these couple windows here. So in addition, within the RDWYII utility properties, the HGL elevation is shown under the results upstream structure. So here we can confirm that the hydraulic grade line of 692.95 is lower than the roadway elevation, and the 100-year flow will not overtop the roadway. So that we have looked at all the hydraulic data, let's open back up the main Road2 BC drainage model file. And you can delete the copied file since it cannot be reopened now. And be sure to select No on Compact Database. Lastly, we need to size and lay out the wing walls for the proposed box culvert according to the TDOT standard drawings. So designers need to locate the applicable standard drawings for the proposed box size. For this exercise, we will go ahead and open the STD 17-53, which is the applicable standard drawing. From the standard drawing, we need to pull some information by selecting the maximum fill height. So in this scenario, the box culvert will be around 10 foot of fill. So from that, we're going to have the top of slab width, or ST, be 9 inches, the bottom of slab width, or SB, be 9 inches, the exterior wall width, or WT, is 8 inches, and the out-to-out width, or BW, is 9.33 feet. So then we need to locate the applicable wing wall standard drawings for the proposed box culvert based on the structure skew and slopes of the proposed roadway at all 4 corners of the box. The wing wall standard drawings are STD 17-11 through 17-14. For this exercise, the box culvert is at a 90-degree skew to the proposed roadway, so STD 17-11 is the applicable standard drawing. The proposed roadway has 4-to-1 slopes, and the box height is 8 feet. However, that is the cell height and not the box height. Our box is under about 17 foot of fill, so we need to include the height of the edge beam as well. So from standard drawing STD 17-7, we will determine that the height of the edge beam is 1 foot. So we need the height of the edge beam and the ST dimension to calculate the height of the wing wall, which equates to 9.75 feet. To be conservative, we will round up and use 10-foot value for the length of the wing walls. So from STD 17-11, we will need some of the dimensions. So note, for scenarios requiring at least 1 foot of embedment per Chapter 6 of the TDOT Drainage Manual, ensure that the proposed box culvert and wing wall heights account for this embedment. Likewise, the proposed inverts need to be adjusted 1 foot down from the hydraulic inverts to place the box correctly. So from that standard drawing, we need to know that H, or fill height, is 10 foot, the wall length, or W, is 18.5 feet, and the wall height, or H, is 6.5 feet. So now let's select the TL RCBC outside element template. And again, that's under Design, Roadway, 3D Template Points, Drainage, and then Box Culvert. So now let's open up that Place Smart Line, or even the Place Line tool under Drainage and Utilities, Drawing, and Placement. And we're going to draw a 190-foot line down the center line of the box. And then we're going to offset that line 4 foot on both sides of the center line, which represents the outside width of the box, or 8 feet. And then once we have those two outside lines drawn, we can delete the center line. And the inside dimensions will be used since that is what controls the wing wall templates in the next exercise. So using the same line tool from the previous step, connect the ends of the box culvert to create the closed shape. And note that this shape does not have to be complex, it is only used as a guide for modeling. So next we need to draw the wing walls. So according to STD 17-10, the typical corner details, the wing wall will have a 1 foot lip that extends out from the box. So now let's draw a 1 foot extension outward from the ends of the box on all 4 corners. So to do this, I'm going to use the Extend Line tool under Drawing, Modify, Vertex, and then Extend Line. The skew angle is with respect to the roadway centerline, so we need to draw the wing wall at 45 degrees from the box culvert skew. So to do this, we need to rotate the view along the length of the box culvert, if it's not already. So the wall length should be 18.5 feet from the 1 foot extensions. So open the place line tool, which is under Drainage and Utilities, Drawing, and then Placement. And then for the upper left wing wall, draw a line 18.5 feet at N45W angle, or north 45 west. Then repeat the last step for the remaining 3 wing walls, keying in the applicable angle. So since we know that the existing box inverts work, we need to create a profile for this box culvert. So let's go ahead and open up that Stream 5 RCBC profile, and then we're going to delete the 3D cut if it's still there. So to delete this 3D cut, hover over the 3D cut border and then select the red X in the heads up display. So the profile should already have the active terrain in it. So go ahead and select the RCBC-centerline feature definition under Linear, Roadway, Drainage, and RCBC. And now we can go ahead and switch back to that open roads modeling workflow. And then let's turn on that Civil AccuDraw for the profile, and then we can open the profile line between points tool under Open Roads Modeling, Geometry, Vertical, and Lines. So here we want to key in the start and stop values for the box culvert inverts. So here the first one, we want the station to be 0 and the Z to be 691.77. And then left click to place that point. And then the end point needs to be 190 at an elevation of 689.98. Then left click to place that point. And then we can set this profile line that we just drew as active. And then now the drainage portion of the modeling of the box culvert is complete. We'll now have to set up the plan view layout to model the box culvert in 3D. And this concludes exercise 12.4 box culvert utility model and analysis.